All right, welcome. For this problem, we're going to be, or for these concepts, we're going to use a problem that describes constant acceleration. And with that constant acceleration comes some terms that we refer to them as kinematic equations. So let me write those out first. Kinematic equations. So similar to the previous videos that I've described, I'm going to teach these concepts within the context of this particular problem, so that you can use these concepts in any particular problem that happens to have constant acceleration. Okay, doing it this way, it gives us some focus for the problem itself, but hopefully keeps it open enough in terms of concepts and understanding so that you can then apply it to other situations. Okay. So I actually want to remove this kinematics. I want to put it over on the other side. So, so the first thing with constant acceleration means that, so I guess that's what we need to start with. Sorry. So constant acceleration is defined as, constant acceleration means, right, that the change in acceleration is 0, right? It's not changing with respect to time. It's not changing at all. The change in acceleration, specifically in the x direction, because we're dealing with one-dimensional things in this particular problem, is equal to 0. Okay, if that is the case, if the acceleration is constant, right? So it means that some initial acceleration equals some final acceleration. If that is true, then that allows us to describe a system of equations known as the kinematic equations. And those kinematic equations are very important because it is specifically that. It allows us to describe how position, velocity, acceleration, and time are related together in a nice, convenient package. And the equations that we have, where's my mouse? There we go, are as follows. We have that the final velocity is equal to the initial velocity plus the acceleration times time, right? This is just derived from the average acceleration equation, just a little bit of a rearrangement. The second is that we have some final position is equal to an initial position plus 1/2, oops, not yet. Where's my, there it is. Plus the initial velocity in the x times time plus 1/2 ax t squared. And that comes from integration of the definition of our acceleration. Then if we do this, we can get a relationship between the velocities, the square of the velocities. Again, these are the x positions, plus 2ax delta x, or the change in position. And the last one is another position here, where we add together the velocities and the x and multiply that by time. Okay, so this is another way, or these are 4 ways that we have to relate them together. Now the cool thing about it is that, the cool thing about this set of equations, I keep losing my mouse here. There it is that all of these, each one of these pieces is missing something that the other one does not have. So for instance, this third one, where we have v final squared is equal to v initial squared plus 2a delta x, does not have time, right? So if in a particular situation we have a problem that we don't have time, but we have these other things, then we can solve for time in one thing and use it in the other. So it's a cool way to go about this, and hopefully we get to see that here. So here's our setup. All right, so now let's go to the problem. Here we have a ball that's thrown straight up with some initial velocity. We're standing on a ledge, so we're going to draw a picture here. So here's our ledge. Here's the ground. Oops. Here's the ground. We're standing on the ledge, and we throw this ball up into the air. It's thrown straight up. All right, it's thrown straight up with some initial velocity. We're given that our initial height is some height above the ground, which means that we have now established that this ground here is at a 0. And that's very important, as we'll see in just a second. We're also given that this ball has an initial height of h, or that we are at some height of h. Okay? It travels upward to some maximum height. All right, so the ball reaches some height, some max height, so we'll call that h max. And that it takes it a time of t max to get up there. Okay, so from this position, so covering this time, it takes a time of t max. All right, we're then told that it reaches the ground, so the ground is actually our final position. Oh, I said x, I meant y, I'm sorry. So let me just change this really quick. Right, so that's our y, so that's our height. So our final y, the ball is has made it up, it's turned around, and it's come back down and reached the ground. Okay, and that the time that it takes to go through that whole thing, or the total time, is equal to 2 times the time that it took for it to go up from its initial height to the top. Okay, and our end goal is what is our initial velocity in terms of h. Right, so what that means is that, again, we don't have really any numbers here. What we're looking for is velocity that is written out specifically as some number times h. That's all we care about, some initial velocity. Okay, so just to clarify a couple things here, we are still in one-dimensional motion because we're now going up and down. Okay, so that means that all of these velocities are y's. All right, so this is initial velocity in the y direction. This is a height of y naught or y final. So we have these different positions. Okay, which means that I guess I wrote out these kinematic equations a little prematurely, I guess, right? But because we're in a constant acceleration, then our acceleration is going to remain the same, and our kinematic equations can now be transferred to the other direction, which is y, right? So they're the same thing, but now instead of being sub x or x final, it's now sub y or y final. Okay, so those are the two. Those are the two things. So these are the tools that we have to now put this all together. There's two other things that we need to know about in order to complete this problem. The first is what is happening in this. So once we release the ball has a velocity, but what is acting on the ball in order for it to go up some height, stop, turn around, and come back down? And that is gravity. Specifically, g is the acceleration of gravity, and I guess I should say g, the negative j hat direction. right? Because this is a sub y, okay? But it is acting on the ball at all times, right? Once we let it go, the only thing that's acting on it is gravity, and gravity doesn't change. It is constant, and it's a constant acceleration with this particular problem. So that means that we are capable of using our kinematics. But there's also one other thing that happens here. What happens to the velocity at this peak point? And it's very important, right? The velocity here, and we can look at it. We let it go with some initial velocity, but it's at that peak point. The peak point is defined at when the velocity at that max does what? Turns into 0. That's the point at which the ball then turns around and it now starts to move down, because notice our initial velocity is in the positive direction. This is assuming that we have a positive y up and a negative y down, right? So for up, or I guess I should say positive j hat, and this is a negative j hat, right? So initially we have a positive j. At the end, right, this final velocity is going down in the negative j hat. Right? It's going in a negative direction. So that means that if our velocity and our acceleration have different directions, that the velocity is going to decrease until it then turns around and matches the direction that the acceleration. If the acceleration acts on it long enough, then that's what will happen. Otherwise, what you get is a decrease in the velocity, right? And that's what happens, because we are decreasing in our velocity up to some 0 point, and then that velocity turns around and continues to increase until it runs into the ground, basically. So these are all very important concepts here. So this is constant acceleration, specifically gravity, and we'll call it negative g in the j hat direction, and it's negative because it's in that direction. G, the acceleration due to gravity, is defined as 9.80 meters per second squared. Notice that I did not say negative 9.8. The negative comes from the direction. So if you've watched any of my previous videos, we've talked about the idea that we can change and move our coordinate system to whatever we want it to be. So if we actually took our coordinate system and flipped it and pointed the positive y down, then we'd have a positive acceleration due to gravity, or a value, I guess. So gravity itself is just some number, 9.8. It doesn't have a direction. The direction comes from how we have aligned our axes. All right, and that's a very important point. So we have acceleration that is constant. If the acceleration due to gravity is the only acceleration, then we have a special circumstance where this is called free fall. So if gravity is the only acceleration that's acting on some object, then we are what's called in free fall, which is nice because there's going to be lots of situations where we are in free fall. But this is one situation. What was the other point? Oh, so the other important point here is that the velocity at the peak or the max, so whatever one is referenced, the velocity there is 0. This is typically in the y direction. Okay, so sometimes you'll see it as v peak, sometimes you'll see it as v max. Whatever that is, the velocity is in 0 because that's when it's turning around and coming back down. All right, so those are the concepts that we use to solve any constant acceleration problem. And then if it's specifically in free fall, then we can use gravity as the constant acceleration. If it's not, then it's not in free fall, but we will still have some constant acceleration that we can use these equations for. So now we're going to manipulate these kinematic equations a bit so that you can see how everything fits together. Okay. So this is an interesting problem because they give us these times. They give us these times, which allows us to analyze things in a very interesting way, I think. So what we're going to do is divide up this system of equations into two parts. The first part we're going to do from when the ball is released to the peak. And why would I do that? Because, and if you watched any of the other videos, it's for convenience, right? At the peak is a very, very convenient place because the velocity at that peak is 0. But they also give us time between when it's let go to when it reaches its max. And so that gives us a nice point at which we can break things up. So let me just make a note here. So we're going to break problem or situation into two parts. The first is from our initial position to the max position. That's going to be our first. The second is going to look at the max down to the end. Okay. For each of these, we have a, well, no, I guess we don't have the whole time. I guess we only have that time, but that's fine. Why isn't that coming down? Okay, so let's look at the first. So for the first part, lost my cursor again. There we go. So for our number 1, we go from our y naught to our y max. We can write out all of the kinematic equations. So let's do that. So we have, in this case, we're going to have our v final be our v max. Okay, so we are going to have our v max in the y direction equal to our initial velocity in the y direction plus our acceleration in the y direction times t. The next equation is our y max is equal to our y initial plus our initial velocity in the y direction times t plus 1/2 our acceleration in the y direction times t squared. Next, we have our velocity final, our velocity final, which is actually our velocity at the max point squared, is equal to our initial velocity squared plus our 2 times our acceleration in the y direction times our change in y. And then we have our y max is equal to our y initial plus 1/2 v max plus v initial y times time. Okay. Now, this is a lot to write it all out, but I think it's very important because it gives you practice in seeing how things are all playing out. And I forgot that we actually have a time that we can put in here. Lost my cursor again. There it is. Where our t is equal to this term that they gave us as t max. So we can go through and substitute that in just a second. But first, we're going to go through and highlight everything that's 0. Specifically, the maximum velocities are 0. So these are all 0. This is 0. And we have that our acceleration, right, we know this too, in the y direction is equal to negative g. Again, negative because of the direction that we've said. We've said that down is negative and the acceleration is pointed down, and so it's going to be a negative. So that means for each of these accelerations, we can substitute in the negative g, this, negative g, this, negative g. We also have that our t is our t max, right? So we can substitute that in too. This is t max, and this is t max. And that our initial velocity, the last thing, initial velocity in the y is just our v naught. Okay. So let's rewrite all of these. These all will now give us 0 is equal to our v naught minus g t max. That's for the first one. The second one is our y max is equal to our, oh, I guess we have a y naught too. Wow, we have a lot of information. Our y naught is h plus our V naught T max plus 1/2 negative G T max squared. Then 0 is equal to V naught squared minus 2G. Now in our delta X, that's our H max minus H. Technically, we don't have H max, I guess. And then we have our Y max. I guess I should keep it Y max because that's what I have there. H, so I'll change that in a second. 1/2 V naught T max. Okay, I'm going to take out that H max because we technically don't have that. We just have that in terms of Y. All right. Okay, so now we can go through and say, all right, what equations do we know basically everything, except I guess we're looking for our V naught, right? But this one we can this first one we could rearrange fairly simply. Well, let's do that first, I guess. So this we have that V naught is equal to G times T max, right? Or the amount of time that it takes for it to be released up to some height, which takes a given amount of time. So that's pretty nice, okay? And we're gonna hold off on these other ones just for a minute, okay? But that first one is nice and convenient, okay? So now let's look at this second part. We are going to look at when we're going to start at our initial and we're going to make our final at the very, very end. And that's a little bit different than I have here because I meant to put this as the initial, not from the max. And the reason is because we have a time that goes from the initial to the end rather than the max to the end. So let's see how this now all works out. Let's write this out. So we have, again, our initial velocity in the y direction is V naught. Now our time, instead of being T max, is now T total. Our acceleration in the y direction is still negative G. So from the very beginning to the very end, it's still negative G, the whole thing. Our initial velocity, or I'm sorry, our initial height is H. Our final height is 0, because that's where we're referencing everything from. And we have some final velocity, which is some final velocity in the y. Okay, we don't know what that is. So I guess this is an important point too. When we do this analysis, we do not take our final velocity as 0, because as it reaches so if this is the ground and this is the ball, as it reaches the ground, just as it hits the ground, just as it reaches 0, it still has velocity, because what's going to happen to that ball is it's going to crunch a little bit, and then if it bounces at all, it'll get bounced back up. So there's, as we'll see later on, there's some momentum happening. And so we take our velocity to be right as it's coming into contact, which means it's not 0. Okay? If it sits there for a long time, blah, 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 then it will become 0. But we're not taking it as it's sitting there a long time. We're taking it just as it reaches that ground. Okay? So now we're going to rewrite these kinematic equations. We're going to do it again. We're going to write them all out. And this is how I suggest you do it, because you can start to see how things fit together, and you can do any sort of kinematic problem if you can find your cursor. There we go. All right, so here we go. We have our V final, which we don't know, in the y direction, is equal to our initial velocity plus our negative G times T total. Okay. Our final position is 0. Our initial position is H. Our initial velocity is V naught times the time that it takes for it to go up and down, plus our 1/2 negative G T total squared. Next, we have some final velocity, which again, we don't know. It's equal to the square of the initial velocity plus 2 negative G, and in this case, we have a final minus our initial position, which is just negative h, which is nice. And then again, we have our final position is equal to our initial position plus 1/2 some final velocity plus our initial velocity times the total time. Now, what we want is our initial velocity again. So this is just a reminder that we want our initial velocity in terms of h. So this means proportional to. We want to know how, or I guess it'd be more like this. How is it proportional to h? What's the relationship between our initial velocity and h, right? But there's one key thing here that we're also given. And specifically, we're given that the total time that it takes is 2 times t max. Okay, and now this is going to be the key. So what we're now going to do is substitute our t max, or our 2 times t max, into our total times here in each of these places. Okay, so now we get something that looks like this for each of them. V naught y minus 2g t max. This next one, we get 0 is equal to h plus v naught 2 t max minus 1/2 g 4 t max squared. Our final velocity, which again we don't know, so these ones aren't going to be necessarily helpful, but that's okay. 2gh, so those negatives all cancel out, so we get a positive there. And then we get 0 is equal to h plus the 1/2 goes away. So we have v final plus v initial times t max. Okay, so hopefully you're starting to see how this is all, how we're going to make this all work. All right. Okay, so sorry, I'm trying to get my cursor down here. It's not pulling me down at all. There we go. All right, so again, we want our initial velocity in terms of h. Okay, so there are some extraneous things that we have in here, particularly this velocity, this final velocity. We don't really know about it, and at this point, it doesn't seem like we can use it at all. What we're trying to do is, again, get our velocity in terms of h, but without anything else that we don't know. And be careful how to say that. We want to get velocity in terms of h with only things that we know, right? So if we now go in here, we can now look and see that there's specifically this one equation in which we have information that we know for everything. We know h, we want to find v naught, we know t max, and we know g. So that allows us to now take this equation. I'm going to write it out just so we have it. Well, I'll just keep it as it is. So now we can look at this equation and say, okay, if I want to get this initial velocity in terms of h, this may be the way to go because I have a v naught and I have an h, but I have this issue that now I have this v max. Okay, or not this v max, this t max. But from up here, look what we have. From up here, we have a relationship between t max, g, and v naught. So what I can actually do is solve for t max, and t max is equal to v naught over g. I can now plug in for t max, and I can get this equation to now be only in terms of constants and h, so and v naught. So h is equal to 2 V naught, if we plug in T max, we get V naught over G minus, oh look, there's a 4 and a 1/2 there. That's silly. 2G times T max squared, which is V naught squared over G squared. How come this isn't working? All right, so from here, well, why isn't that working now? There we go. All right, so I just went back through and looked at the problem that I copied this down, and I copied down the wrong value for the total time. It should be 3. So this should be 3 T max, which means that this should be 3 T max, and this should be 3 T max. This is no longer 4, it's 9. And then this would be 3/2 out front here, which means that this is going to be a little bit different over here. So it was, I mistyped, which is too bad because it makes things a little crazy now. Not crazy, just messed up. Okay. So now this should work a bit better. Did I get it all? So if you notice what was happening there is that all of a sudden I ended up with 0 is equal to h, and that couldn't work. So here we have 3v times v naught over g, great, and then we end up with 9/2 v naught. Okay, that should do it now. Okay, great. So now if we simplify this, whoo, that was crazy for a second there, is equal to h plus 3v naught squared over g minus 9/2 v naught squared over g, which means we can simplify this. If we bring h to the other side, we get negative h. And if we pull out v naught squared over g, we get 3 minus 9/2. All right, and the way that we do this is we multiply both, or multiply this 3 by 2, so we get 6 over 2 minus 9/2, which gives us, you can see it, right? So this is equal to negative 3/2. So that means that we now have negative h is equal to v naught squared over g times negative 3/2. The negatives cancel out. We bring over the, oh, scoot this down so you can see what's going on. There we go. We bring the 2 and the g and the 3 to the other side, so we get 2gh over 3 is equal to v naught squared, so that our final answer is v naught is equal to the square root of 2gh over 3. And that is the relationship between our v naught and the height at which we start, right? So another way to write this would be our v naught is equal to, if we take out, if we do 2/3 g times h to the 1/2. Okay, so again, I'm sorry about that. I did not understand what was going on. So I'll come up here and change this for us. This should be a 3, not a 2. Oh, can I just do it in text? Ah, I can. 3. We'll do it again down here so that we're all on the same page. There it is. So very important that you copy down the problem correctly. But hopefully that gives you a good sense of how we do this, right? So again, the point is that we were able to divide up our kinematic equations. We can divide them up really however we want. In this case, we had an acceleration that was constant throughout, and so that was nice and convenient. But because we were able to divide that out into the times that we were given, the t max time and the t total time, and a relationship between the two, then we're able to get a nice, straightforward, simple relationship between the initial velocity and the height. So thank you. Please review this. Let me know if you have questions, especially here at the end when I obviously copied down the problem incorrectly, but it shows you that t max cannot be, or t total cannot be twice t max, because then you get zeros and that doesn't work. So thanks. Let me know how it goes, leave comments, and I can answer your questions. Thanks.